carbon dating. Okay. As I taught 2 classes before, I think I already taught 2 classes about the linear model of the differential equation. To apply this linear model to a very specific the problems like bacteria and decay, okay, something like that. And today we're gonna talk about the carbon dating. We have a very specific one. Libya half-life. It's a half-life of C14 has was approximately 5,600 years. Okay. And another one is Cambridge. Half-life. And half-life of C14 was approximately 5,730 years. Okay, so we have 2 different half-life. One is Libya, and another one is Cambridge half-life. And the first one is 5,600 years, and the second one will be 5,730 years. So let's take a look at the questions. One, a fossilized bone is found to contain 0.1% of its original amount of C14. Determine the age of the fossil. Okay. In this problems, we decide to use Cambridge half-life. Okay, we're gonna use Cambridge half-life. And the first of all, we're gonna build a linear model, as I mentioned before. For this linear model, we can write down as dA over dt Ka. Okay, that's the linear model. K is the coefficient. It can be a growth, or decay, right? Can be a growth or decay. And then for this case, we can say that is the decay, okay, decay. And now let's take a look the conditions. First of all, initial condition, we assume that is A0. And the second one is the half-life. So it's 1,730 equals original half, right? That's the 2 conditions, okay? As we can know from the previous example, we know The solution of this ODE can be written down as what? It's A equals what? CEKT, right? We already did several examples how to solve this type of problems. We can use separable method, right? And we can get the solution is here. Here I just copy it, copy it. Okay, now we're gonna plug in these solutions. The first one is 0, right? 0 is 0. So E K times 0 equals A0. The second one is what? Is T equals 5, 7, 30. That equals 1/2 A0. Okay, we got this one. And from the first one, we got a C equals A0, right? And plug in here. One half. And use your calculator. That divided by that is roughly equal to negative 0, 0, 0. Okay, we got this K. Now we can see, plugging back, C is A0. Okay, that is the solution for this guy, the whole IVP problems. Okay, now from these problems, we want to contain 0.1% of the original one. 0.1%. That means we have 0.1% of A0, and we want to find out the K. Oh, sorry, this is T. Okay, so 0.0%. That means we need to find the T, right? We plug in the 0.1% of A0. And as you can say, 0.0 will be 0.001. Cancel that. And use your len, right? Len of this guy divided by negative 0, 0. And this will roughly equals 57103 years. Okay, so that's the answer. That's it. So that's gonna be the last example for the this chapter. And today we're gonna move to the chapter 4. And we're gonna learn some different things. Okay. Okay, so let's take a look. Chapter 4. Theorem. Theory of linear equations. The initial value problems. I'm gonna write down the initial value problems again. Probably some of you already forget it. Initial value problem for a linear differential equation and nth nth order initial value problems can be written down as this way. Is here anx dn dy dx an1x dnyy dxn plus dy over dx a0x y equals gx. And of course, we have y0, y1. For the nth order, we're supposed to have n initial conditions, right? So here we have n initial conditions. And be careful, here we start with y, right? Starts y x0 and y prime until y n minus 1. So we total we have how many n initial conditions from the 0, 1 to n minus 1. So n initial conditions. Initial conditions. Okay. Be careful. Here's n, right? From 0 to n minus 1 should be n initial conditions. It's not n minus 1. Okay, so let's take a look at the theorem. 4.1.1 existence of a unique solution let anx an minus 1x and gx be continuous on an interval on and let anx doesn't equal 0 for every x in this interval if x equals x0 is any point in this interval any point in this interval then a solution yx of the initial value problems 1 exists on the interval, and it's unique. And it's unique. Okay, so now I give you guys a very specific theorem to prove that initial value problems has a very unique solution. Okay, so what kind of condition? So first thing should be continuous. Okay, what do we mean the continuous? There's no breakpoint. Okay, so an minus one, a1, a0, gx, all the coefficients should be continuous. There's no kind of singularity between these functions, singularities. Okay, or you can say, hey, we can draw a curve for each functions. Okay, the curve is smooth. That means continuous. Continuous. Okay. Now let's take a look. Is a very specific example. Is the trivial solution. And we're going to prove that is unique. And this solution is unique. How to prove it? We're going to use the theorem. Okay, use the theorem. Now let's take a look. First things we can see A3x is A3x, right? A2x here, A1x, A0x. So we can tell A3, A2, A1, A0 corresponding to this coefficient. They are, and Gx is 0, 2, are constants. So they are continuous. They are continuous on interval R. Okay, they are continuous because they are constant. If there's a constant function, it's horizontal line always continuous, right? Continuous. Then x equals 1, and we can say x equals 1. That's the initial condition, right? Initial condition. X equals 1. Here the x equals x0. X0 is initial condition. X is equals 1, right? So x equals 1 is in this interval R. So the solution, solution y equals 0 is the unique solution to unique solution on any interval containing x equals 1. X equals 1. Okay. So based on the theorem, 4.11, we prove that the guy has a unique solution. Okay, unique solution. It's very straightforward if you follow the theorem. Now, let's verify the solution of IVP. Okay, so let's take a look. Example 2. Again, I'm gonna give you guys this example. Let you guys try it. So verify is this guy is the solution of IVP. Solution of IVP. Okay, and also prove that it's unique. Okay, prove that. Check whether this guy solution is unique. Okay, so how to verify this guy is the solution of this IVP? The first things we're gonna verify this guy, right? Verify this guy. How to verify that this guy is the solution of this ODE? We let the left-hand side is y double primes minus 4y. Plug in this guy to do the double derivatives, right? Plug into the left-hand side and plug in the right-hand side. Whether the right-hand side, left-hand side equals right-hand side. If equals to each other, that means that's the solution. And also you need to check the initial conditions. Check x equals 0, whether this guy equals 4. And check the derivative, whether it's the derivative, do the derivative firstly, and then plug in 0, whether the first derivative equals 1. Okay, so basically you're going to check two steps. The first step, check this guy is the solution of this ODE. Okay, and the second one, you need to check the initial conditions. Okay, try it. I give you guys 2 or 3 minutes. Try it by yourself. Okay. One more minute. Okay, one more minute. Okay, I'm gonna do it on board. So for these problems, the first thing we're gonna verify the solution is this guy is a solution of ODE, right? So left hand side, we have what? Plug in. Okay, and then we do the derivative. Be careful, here's a double derivative. So we're gonna do the derivative one by one, okay? So the first derivative of this guy equals itself because it's a composite function. And the derivative of this guy will be this one, and it's a composite function, right? Composite function, we're gonna do the derivative. The whole thing equals itself. Oh, sorry, it equals itself, right? And then do the derivative for this composite function, -2x. And do the derivative of this guy will be very straightforward. It's -3. And this guy will be okay. Now, this guy, you do the derivative of this guy will be 2. Right? And this guy will be what? -2x. -2x will be 2. So we're gonna get derivative of this guy constant is 0, right? Is 0. Okay, so we're gonna get here is here is -12 e2x. Copy it. And here is 6e2x, -2e2x. So let me check whether I make a mistake or not. Oh, sorry, I make a mistake here. Here is a 2. I'm gonna simplify it. We forget one important. Okay, we just do that one derivative here, right? We have another derivative. We'll do the first derivative. We got here's a 2, here's a -2. Here's -3. Now we're going to do the second derivative. So the first derivative, we're going to get, this is a 6. And again, we use the composite function. Right, composite function. And the derivative of 3 is 0. And here is still 2, right? So 2 is 12. -2, -4. Next, we're gonna get okay, very good. So we have what? We have this guy. We're gonna cancel out. Cancel out 12x. 12x, right? And this guy equals the right-hand side. We just prove it. We just prove it. Okay. Now we're gonna check the initial condition. The first initial condition is very straightforward. It's y0 equals 4. That means x equals 0, y equals 4, whether y equals 4, right? So let's check it. Y0, plugging in 3, 2 times 0. Here's a 3 plus 1. Here's a 0, is 4, right? That's exactly equals this one. So that's initial condition is satisfied. For the second one, you need to be careful. We need to do the derivative firstly, because here's a derivative, right? So we do the derivative of this guy. Actually, we already did it here, right? We already did it here. First the derivative. I can show you again. Derivative of the first term. Derivative of second term. Derivative of third term, okay? And we have 3e to x, that is 2, that is -2. And that it should be 6e to the power 2x, -2e to the power -2x, 3. Now you can plug in the 0, 0. Okay, when x equals 0, whether this guy equals 1. So plug in 0. We have 6e to 0. Here's a 6 minus 2. And we're gonna get 1, right? 1. So this condition is satisfied. So we verify this guy is the solution of this IVP. Now we're gonna check whether this guy is unique or not. As we can tell, the coefficients here are constant. Right? You can see A2x, A1x, and A0x. So A2x is 1, A1x is 0, right? Because we don't have the first derivative. A0x is -4, and the gx is 12x. We don't have a singularity issue for the 12x, right? So continuous interval X equals 0 is in this interval R. Okay. Therefore, y equals minus 3x is the unique solution on any interval containing x equals 0. Okay, so that's the problems. That's the problems. Okay, that's the problems. Let me check whether I have some more examples. Okay, let's move on. Let's move on. We already addressed the initial value problems, and we also going to learn a very special problems we call the boundary value problems. Okay, boundary value problems. For the boundary value problems, basically we have two conditions, and we don't have the very derivative for x0. For x0, basically we have two different points. For the initial conditions, we have what? We have only 1 point. 1 point. For example, here or here, x0, right? And if we add the conditions, we'll just do the derivative. Okay, do the derivative. And for the boundary value problems, we're gonna have 2 points at least. Okay, 2 points. So let's take a look. The definition of boundary value problem. We have ATX dy over dx square a1 dy over dx a0. Okay, that's the typical linear second order linear ordinary differential equation. Okay, and we have two conditions. One is y a equals y0 and yb equals 1 y1. Okay, so as we can see here, we have 2 points. One is a, another point is b. Okay, it's a different from the initial condition. Initial condition always has 1 point, x0, right? Here we have 2 points. We can say 2 points boundary value problem, or a boundary value problem, BVP. We call it BVP. And of course, while A equals Y0 and YB equals Y1 are called boundary conditions. Okay, BC. Now, for second order differential equation, we have other pairs of boundary conditions. For example, let me take a look. For second order differential equation, we have other pairs of boundary conditions. The first one will be like that. The derivative y0, yb equals y1, 3. Or you can say okay, we can have different pairs of initial conditions. Yes, different pair initial conditions. Okay, or boundary conditions. And we call this is a boundary condition because we have 2 points. Okay, A and B, right? So totally we have 4 types of boundary conditions. Yes, here's another important things. If I give you the pairs of boundary conditions, it doesn't mean, and this one is pretty important, it doesn't mean BVP, boundary constraint problems, has a unique solution. Okay, so if I give you 2 boundary conditions, doesn't mean this guy has a unique solution. Okay, that's totally different from the initial value problems. If I give you initial problems and I correspondingly I give you the initial conditions, and if the initial conditions satisfy what? Satisfy this theorem. Okay, satisfy this theorem, we can say we have a unique solution. However, for the boundary value problems, it's not necessary. Means that BVP has a unique solution. If I give you these 2 boundary conditions, okay, that's a very important thing. Now let's take a look at the first example. Okay, the first example is here. Design 14. And it's the solution of this guy. Now, I give you two boundary conditions. Okay, two boundary conditions for this guy. The first boundary condition is x0 equals 0 and x pi over 2. Okay, now let's try it. Because we already claim that guy is a solution of this ODE. So the left work, we just needed to double check these two boundary conditions and find out the C1 and the C2. Okay, that's a strategy. So how to find the C1 and the C2? Just plug in. Huh? So plug in when t equals 0. Plug in t equals 0, that equals 0. Right? That's the first condition. Second condition, when t equals pi over 2, that guy equals 0. Okay. Now we can simplify it for the first condition. Cosine 0 plus C2 sine 0 equals 0. We know cosine 0 equals 1, right? 1 times C1. And sine 0 is 0. 0 times C2 is. So we get the C1 equals 0. Now, from condition 2, we can see that is cosine pi over 2, right? Pi over 2 plus C2 sine, sorry, it's not a pi over 2. 4 times 2, so it should be cosine 2 pi. Right? Cosine 2 pi. 4 divided by 2 is 2 pi. And here is sine 2 pi. As we can see, cosine 2 pi is 1, right? It's 1. So we get 1. Sine 2 pi is 0. So you still get C0. C1 equals 0. So the solution is what? The solution we can write down is plugging back. C1 equals 0, plugging back. This time is 0. We only get sine 4t. And this guy is the solution of BVP. Okay, that BVP consists of this ODE plus this condition. As we can say, we don't have unique solution here. C2 can be any real number. Did you see it? C2 can be any real numbers. So that means we have infinity solutions. Infinity solutions for this case. Okay, for this case, we have infinity solutions because C2 can be any real number, and these two boundary value problem doesn't give us a very unique value for the C2. Only give you the C1 equal to 0. So when you plug in back, we got this solution, right? We got this solution, and this solution we have infinity solution. Okay, so let's go back here as I claimed. If I give you a pair of boundary conditions, doesn't mean BVP has unique solution. Okay, so be careful. Okay, time's up. I'm gonna wrap it up class here.